Hello, everyone. So this presentation is about increasing water vapor in the stratosphere and the mesosphere observed by satellite. I first briefly introduce the CEDAR water vapor data and give some impact of the long-term changes of water vapor in the stratosphere and the mesosphere. Then the results of linear trends and solar cycle variations in SABRE and MLS water vapor, followed by the comparison with the vacuum results. So here's a list of SABRE level 2A routine data products. We know that SABRE has been taking data since 2002, has been a very long, healthy spaceborne measurement. It can measure a number of parameters in the stratosphere, mesosphere, and lower thermosphere, including temperature, pressure, neutral density, and many other composition, including the water vapor from 15 kilometers to 90 kilometers. There's some validation work by comparing SABRE water vapor with other satellite measurement, MLS, ACE, and MEPAS. We can see that the global distribution of water vapor observed by different satellites are very consistent. They reach the peak at about 1 hectopascal to 0.1 hectopascal. And the mixing ratio decrease with altitude in the mesosphere because social photo dissociation. In the polar region, during very strong descent event, we can see similar decreasing water vapor in winter. So this slide starts to give the motivation why we need to study the long-term changes of stratospheric water vapor. First of all, the Sulan-Solomon science paper in 2010 shows that the stratospheric water vapor is a very important greenhouse gas in the lower stratosphere. If we take a look at the right hand figure, this gray area is a contribution of radiative forcing contributed by the stratosphere water vapor. So it's not negligible. Another implication of stratosphere water vapor is it actually influences heterogeneous chemical reactions that destroy ozone in the stratosphere. According to the recent Lupkin GRL 2018 paper, it shows that the increasing sighting, increasing abundant polar mesospheric clouds in the summer polar region is causing by more water vapor. And this water vapor in the mesosphere comes from methane. oxidation. So in this simulation, spanning over 100 years, the red curve is increasing carbon dioxide, but constant water vapor. And the black curve shows increasing carbon dioxide and increasing water vapor. So this clearly shows that the increasing polar mesospheric clouds are mainly caused by increasing water vapor rather than increasing carbon dioxide. So this is our results, which is published last year GRL. We compare the time series of global mean SABRE and MLS water vapor within 50 south and 50 north. We avoid the polar region because of the SABRE yaw cycle. So SABRE is turning around every 60 days to avoid facing the sun. And this is a running 60-day mean. So it's about the running yaw cycle mean. Starting from the lower stratosphere, both SABRE, which is the red line, and the MLS, the blue line, showing constantly increasing trend. And this increasing goes throughout the upper stratosphere and also in the mesosphere. In the mesopause region, around 82 kilometers, the solar cycle effect starts to take over because during solar maximum, stronger UV photo dissociate water vapor into hydrogen and OH. So during solar minimum, solar maximum, there's less water vapor. During solar minimum, there are more water vapor. We also compare the SABRE and the MLS observations with the famous Boulder Foster Point hygrometers on balloons in the lower stratosphere. So this red line is SABRE and blue line indicates MLS just around Boulder, okay, within 5 degrees latitude and 10 degree longitude. And those cross points are individual frost point measurements. We can see that all three measurements show increasing water vapor since 2003. So they are very consistent. How we calculate the trend of water vapor? First of all, we take bi-monthly mean to remove tides in the mesosphere. Then we did the multiple linear regression, considering the linear term f.7 annual oscillation, semi-annual oscillation, QPO, and ENSO. Here's a linear trend and solar cycle. The left side is the linear trend, is the absolute values. And the right-hand side is relative values, which is the absolute value divided by the global mean water vapor at corresponding levels. Let's just take a look at the percentage changes the relative linear trend, shows very strong increase in trend observed by both CEDAR and MLS in the lower stratosphere, reaching about 5 to 6% per decade. The two measurements diverge in the mesosphere, in the lower mesosphere. The MLS trend is much larger, about twice larger comparing to CEDAR. Remember that the CEDAR vertical resolution at the higher altitude is better than MLS. The solar cycle variation of CEDAR and MLS are similar. There are very strong negative correlation with solar cycle, just as I just mentioned, because of the photo dissociation in the mesosphere. And there's a very weak positive correlation with the solar cycle, which needs further investigation. Could be due to changing dynamics. Is the change of water vapor in the mesosphere expected? We know that the water vapor change in the mesosphere is caused by the methane oxidation following this equation here. So one methane can divide into two water vapor. Therefore, the trend of methane divided by 2 should equal to the water vapor trend. This is the ground-based methane abundance provided by NOAA. See constantly increasing methane. After 2000, methane increases by about 5 to 6% per decade. This corresponding to about 2.5 to 3% per decade for water vapor. CEDAR observed about 2 to 3% per decade. Here's CEDAR. So the CEDAR observation is consistent with theoretical methane chemistry. At last, we compare the CEDAR and MLS observations to the free-run vacuum simulations provided by Rolando Garcia at UNCAR. The left panel shows the relative linear trend. The right panel shows the solar cycle variation. The solar cycle variation between the model and satellite observations are very consistent with increasing negative correlation in the mesosphere. On the other hand, the linear trend of the vacuum water vapor doesn't show very strong increase in the lower stratosphere. It could be due to a lack of physics. For example, like deep convection is not resolved in vacuum. And the deep convection can transport water vapor into the stratosphere from the troposphere. The vacuum simulates also about 2% per decade water vapor increase in the mesosphere. And this is more consistent with the CEDAR observations. And this is a more detailed water vapor trend observed by CEDAR. There are some general features. You can see a strong increasing region in the tropical lower stratosphere. And this is in agreement with the shallow branch of the Brewer-Dobson circulation, where transport water vapor from the troposphere through the tropopause into the lower stratosphere. And there's a minimum of trend in the stratopause region, and increasing water vapor trend in the mesosphere. The increasing trend in the mesosphere is because methane is oxidized in the mesosphere. And this the shaded region indicates 95% significance. And this is a comparison between SABRE and Wacom. As we just showed, Wacom doesn't reproduce the strong increasing water vapor in the stratosphere. On the other hand, Wacom does simulate increasing water vapor due to methane in the mesosphere. The detailed structures they do not match each other. Here's a summary of this short presentation. SABRE linear trend analysis shows very large trend of about 5 to 6% per decade in the tropical lower stratosphere. And this could contribute to radiative forcing and global warming in the troposphere. The trend in the middle to upper mesosphere is due to the methane oxidation and increasing methane abundance. MLS trend support the values detected by SABRE in the tropical lower stratosphere. The Wacom simulations support the trend observed by SABRE in the mesosphere, but cannot reproduce the trend in the lower stratosphere. Some future work, we need to perform line-by-line radiative forcing calculations of water vapor trend on global warming. We also need to study how the increasing water vapor may impact the stratosphere chemistry, like ozone, and also contributions to upper atmosphere hydrogen. Thank you.